how to locate the center of gravity and the centroid for a body having a variable shape. For example, this dinosaur has its center of gravity right over its legs, and that makes it easy for it to walk about. Now, if you want to find the center of gravity through an experiment, here's one way in which you can do it. Take, for example, this triangular plate. If you hang it from one edge and then also hang a string and weight from the same point, you can draw a line along the string. Now take the plate and hang it from another edge and draw another line. The two lines will intersect at the center of gravity. You can actually see this is the case if you were to hang it from a third point. The line will pass through the intersection of the first two lines. Of course, we know that for a triangle, the center of gravity is located at the centroid, or the center point. Therefore, that would be 1/3 of the way up from the base of the triangle, something we've learned from a previous lesson. Anyway, rather than determining the location of the center of gravity through an experiment, we can also find it analytically from many different shapes. And let me explain how that's done. Consider, for example, this thin bar. I can locate the center of gravity of it by simply dividing it into a series of small differential segments, such as this. Each segment has a weight dw, and the distance from the left end of the bar to the center of the segment we'll refer to as x tilde. Doing this, of course, creates a system of parallel forces, and now when I reduce this system to a single resultant force and find the location of that force from point O, we'll be able to locate the center of gravity for the bar. And how do we do this? Well, if you add up all the forces in the system, you get the resultant force. This means we have to integrate from the left end of the bar all the way to the right end. How do you find the placement of the force? Well, we'll have to do that by taking a balance of moments. For example, you'd write the expression this way. The moment of the resultant force around point O is equal to the sum of the moments of all the differential forces around point O. That's expressed by this equation, isn't it? Here's our resultant force times our moment arm, x bar, and here, of course, is the moment of each differential force. If I solve this equation for x bar, I'll find the location, then, of the center of gravity for our bar. And this is the type of formulas we'll be using throughout the lesson. They're a ratio of a moment of a loading, for example, divided by the total loading, to get our placement, x bar, a balance of moments, essentially. Let me now generalize this idea a bit more. Let's say, for example, we have this object of variable shape. I've divided it into a small set of differential size elements, each having a weight dw. And if I take the moment of these differential elements around the y-axis, that moment, of course, would be equal to the moment arm x tilde times dw, and I sum them over the entire object, its entire shape, that is, and I set that moment equal to the moment of w times x bar, I'll be able to locate x bar, won't I? So again, we have a formula which is similar to what we just covered. A moment divided by a total weight, and that gives us the location of the center of gravity, along the x-axis, that is. If I want to find the answer along the y-axis, of course, I'd have to do the same thing by taking moments around the x-axis. Same idea works for the center of mass, doesn't it? I can take a mass element from a body, and I can consider taking the moment of that mass element around the y-axis, summing them up over the entire body, and then dividing by the total mass, and I'll get the position of the center of mass for the body, measured along the x-axis. And finally, we can locate the centroid, or the geometric center, for a volume, or even the center of an area, or a line, or curve. First, though, let's consider the general idea. I take my volume, and I divide it into a series of small differential segments, dv, and I find the moment of each of these segments around the y-axis. That, of course, is represented here. I sum up everything over the volume. And then I divide by the total volume of the shape, and I'll locate my centroidal location along the x-axis. We call that x bar. And again, this moment arm for each of the elements is referred to as x tilde. Now let me be a bit more specific. In the lesson that follows, dealing with volumes, we'll only consider volumes that are symmetric, and when that's the case, we can simplify the integration process. Here, for example, is a volume that's been created by taking and rotating this curve around this generating axis, creating this paraboloid shape. In order to find the location of the centroid of the volume, then, we don't need to deal with three-dimensional volume elements. we can choose a single integration to find the answer. We would do that by using a differential element, which is a disk, like the one you see here. Whenever you use an element like this, then, you want to make sure that this element intersects our generating curve at the arbitrary point. In this case, a distance of y over and a distance of z up. Once you've defined this point of intersection with our generating curve, we can then find what we need when we apply our equation. For example, here I think you see that the centroid is going to be located on the y-axis, isn't it? Because of the symmetry of the shape. In other words, x bar and z bar are both equal to 0, and we simply have to find our distance, y bar, here. And again, it's found from this formula. In order to apply the formula, though, I have to define what the volume of our element will be. That's pretty straightforward, isn't it? The area of the face of the element is pi times z squared, and the thickness of the element is simply dy. Also, we have to locate the centroid for our small element. And that centroid is located right here on the y-axis, isn't it? It's at the center of the disk. And so, what's the coordinate location for y tilde? This distance here, of course, is equal to y, isn't it? So then you'd have all the information you would need. You would have defined dv, and you would have defined y tilde. This is y, and as I said, this is pi times z squared times dy. And then you can carry out the integration. And we'll do problems like that in the next lesson. Now, apart from finding the centroid location for a volume shape, sometimes in engineering design, we have to find the centroid for an area. And the idea for finding the centroid is the same as it is for volumes. The two key equations that we would use to find the coordinate location for the centroid of an area is given by these formulas. They're similar to the ones we use for volumes, aren't they? Here's the moment of the area element around an axis, and we divide by the total area to get our result. In order to solve a problem like this, though, instead of using double integration for the area element, we can use a single integration if we choose a strip of area instead of a small little rectangular shape. And that's what we'll do. Whenever you choose a strip of area you're going to use for your element, you have to make sure that it intersects the bounding curve at the arbitrary point. So that way you can define its size. This, of course, is y up, and it's a distance of x over. Now that it's been located, we can define the area of the element. It's simply equal to y, the height of the element, times the thickness, dx. Also, we need to find the location of the center of the element, and that defines our coordinates, x tilde and, of course, y tilde. So if we know where this is located, this point, the center of the rectangle, center of the strip, we'll have our two coordinate distances. That's pretty easy to get here. The distance from here all the way to here, of course, is equal to x, isn't it? And that's x tilde. The distance from here all the way down to here is y tilde, and that's simply equal to y divided by 2. So we have the things we need to carry out our integration. Our area element, y dx, x tilde, which of course is equal to x, and over here, y tilde, which is y over 2. We don't need to use elements that are orientated this way. We can also use them when they're horizontal like this. But remember that they intersect the bounding curve at the arbitrary point, x over and y up. Again, we need to define our three things that we need. For example, the area of the element. That's simply equal to x times dy. And now the location of the centroid for our small rectangular element. Well, x tilde would equal this distance, x over 2. And y tilde would be the distance from here all the way to here, and that, of course, is equal to y. I'll show application of this idea in one of the next lessons. Finally, let me explain how we can find the centroidal location for a curve. For example, a rod bent in the shape, y equaling a function of x. We do it using these formulas down here. Notice that they're similar to the other ones, aren't they? Here's a moment of a lineal element around an axis, and we divide by the entire length of the curve. For example, in our case, we would choose a small differential element having a length of dl, as shown here. We locate this element at the point x, and of course, y up. This, of course, is the arbitrary location for our element. That's indeed what we need to have. Now, the length of our element, dl, can be related to the length along the x-axis and to its length along the y-axis by using Pythagorean's theorem. Let me explain. If this is dl here, then its projection along the x-axis is simply equal to dx. And along the y-axis, it's simply dy. So here you can see how Pythagorean's theorem actually creates this formula. Oftentimes, we integrate either along the x-axis or we integrate along the y-axis. If we're to integrate along the x-axis, I'm going to factor out the dx from our formula. Doing that would give us this equation. Dx, of course, can be brought back under the radical by simply squaring it. And if you multiply it by this term and then this term, you get this result up here, of course. So all we need to do in order to use this equation would simply be to find our derivative, dy dx, from our function right up in here. Substitute it into here, of course, and then we can put this for dl down, say, in here, and also here. And then we can sum our elements all the way from, say, x1 here, all the way to x2 over here. Finally, we need our distance x tilde for our formula here, and that's simply equal to x, isn't it? Because the centroid of our element is actually right at the element itself, seeing that it's a differential size. And the same thing here, y tilde in our equation is simply equal to y. I'll give you a few numerical examples of how this works in a forthcoming lesson. But for now, though, we'll end this lesson.